Okay, now this is a response spectra that I made for a central earthquake east-west component at 1940. So he said acceleration response spectrum. Okay, so you will get all the information. So now you understand. Okay, this is response spectrum means we plot maximum values only for design, and especially this is for accelerations. Among acceleration, velocities, and displacement, this is for accelerations. Okay, and you see x-axis represented by the period, and y-axis represented by a acceleration and spectral accelerations. We say spectral, right? Spectral means maximum value. Cake design, horse cake design. And what else? As a function of period and as a function of damping ratio, of course. So that if you don't have any damping, which is 0 here, your response is very big, huge, right? And also the building will not stop easily, all right? And you increase your damping ratio from 0 to 20%. 20% is the lowest one. Why? Because your building behavior, building performance, or accelerations gets very small when your damping ratio gets very big, like 20%. Okay? So look at that. Your response spectra is expressed as a function of damping ratio, as a function of periods. Don't forget, that's two. Function of two things, right? Damping ratio and period, and this is maximum value. When your period is 0, what that means, your building is very stiff, as I told you many times, right? So what this is, 0.4 G is PGA, peak ground acceleration. This is what you see on the building is what you get from your earthquake, because your building is very steep, right? Here, and you go to the right side, it makes your building is very flexible. All the acceleration goes to 0. Because your building is flexible, you don't move, right? You're not vibrating because your building moves at the bottom, right? So now you have a peak ground acceleration and you have a 0. Okay, so this is, you're gonna see probably many times before you retire in your area if you're working on building business. And this is very important. And and all the engineers, United States, England, Japan, Korea, they use same response spectra. Okay, so you don't want to forget that if you want work for high-rise building, and this design, seismic design, and these seismic designs are pretty much easy to understand, but you probably don't want to forget this. Okay, okay, and as you're having a peak resonance area is 0.5, so you're on very stiff soil. I told you a resonance plateau, resonance area for 0, for 10%, for 20%, whatever, is a 0.5 when you have a stiff soil, like a rock, something like that. Okay? It depends on what kind of soil, that you want to put the building on, right? Okay, now let's take a look at different earthquake from New Mexico occurred in 1985. Okay, this response spectrum shows you a little different shapes, right? What do you see as a different characteristics of this response spectra compared with one we saw from a central? Can you tell me what's the different thing here? I'll give you a few seconds. Think about it. Okay, your resonance plateau are at longer period, which is 2 seconds, right? You have a resonance plateau at 0.5 seconds for a central, if you remember. But this one has a resonance condition at 2 seconds. Why? Why did this happen? Because of soil conditions underneath of the building in New Mexico. New Mexico is very thick filled in soils, so that your earthquake propagates through the thick soils and create a 2 second dominant period, so that it's going to cause a big resonance response for building over 20-story building right here at 2, right? Why 20-story building that damages? If you remember, the formula that I gave you is that the formula was 1.1 n, right? 0.1 n. N is a number of stories. So n is 20, which is 20-story building. What period you get? You get 2 seconds, right? So 0.1 n formula gets you building period of 2 seconds for 20-story building. So in other words, your 20-story building has exactly as a resonance conditions here at 2 seconds of the response spectrum right here. So you get a damage for 20-story building. Actually, we have a lot of damage around 20-story building in New Mexico in 1985. Okay, so why don't you go and take a look at the damages and all that through the internet for 1985 and make some memo on this note. Okay, and again, even though the different earthquake we are looking at, the definition of response spectra are same, right? The response spectra, what is the definition of response spectra? Again, looking at New Mexico earthquake, is that this represent a maximum response. And then we chose a acceleration for this case, right? The y-axis accelerations. And we say spectral accelerations, we are denoting SA, spectral acceleration, SA. Spectral means maximum value for seismic design, okay? So this is maximum acceleration or maximum velocity or maximum displacement. This case, maximum accelerations as a function of period and as a function of damping, right? For a single degree of freedom system. That's perfect definition, okay? So you don't even have to memorize the definition of response spectra, but you don't want to forget it, because response spectra is essential informations that you want to put them in the computer code like MIDAS, ETAPS, or whatever three-dimensional computer analysis to design buildings, including low-rise building, high-rise building. It doesn't really matter, okay? And this is the way you're looking at the response spectra, okay? Okay, we're gonna summarize today's lecture. Today's lecture is the most important lecture in earthquake engineering, because a building is designed basically based on mostly response spectra, okay? So we're gonna summarize, and I'm gonna introduce how to use response spectra, how to read response spectra. We start calculating period of the building. Okay, we have two ways to calculate period of building. Okay, and we have to know the period of the building to understand and to use response spectra. We have two ways here. The first way, you can use MIDAS. Okay. Second way, we use a approximate equations. Okay. Then I gave you one approximate equations for this 0.1 and okay, we anyway will use one of these two methods to come up with a period of the building. Okay, so this is very easy process. And second, once you get period of the building, you go and determine the damping ratios. The damping ratio, I told you, I gave a brief numbers for low-rise building and high-rise buildings, and depending on the material, steels and concrete building. And you want to take a look at this video clips again to see how you determine damping ratio. If you need, then you have to add a artificial damping. Okay. So let's just, for example, my damping ratio is 5% or 1% for high-rise buildings. So you have to determine damping ratio in second step. In third step, you have to go enter x-axis. X-axis represent what? X-axis represents, right, building period, right? So you go and get started with the x-axis using a period of the building, which is calculated in step 1, okay? Now you're gonna go and hit the response curve, okay? Let's say, for example, if you go into the, let's say 2 seconds here, right? Then you go all the way up. You hit response curve, right? But you hit multiple response curve, a lot of response curve. So which one is yours? You don't know yet? Yes, you know. How? Because you have determined the damping ratio in second step, right? Yes, you know. So say you are having a 5% or 10%, okay? Then this curve is yours, right? Because you know that your damping is 5%, right? This is your curve right there. So now, what's next? What's next? After you hit response curve with your damping, then you go to left, right? You go to left to read a spectral value. So you go to left and to go to get the spectral value here. Okay, spectral value. This spectral value is the value that you're going to use in diffraction calculation of the building and seismic force, shear force. Your Newton's law F equal ma, isn't it? So you know the ma a part, which is from here, right? So this is why you calculate accelerations. Okay, so a, which you picked up from y-axis in SA axis, you go and use that value right here and multiply your building mass. So you get a earthquake lateral load. Easy, isn't it? Okay, this is the probably summary of lecture today after all, right? Okay, let me just repeat the last emphasis one more time before we finish this clip, right? Okay, we get period, we calculate period using one of these two ways, using minus or using a approximate equations. Okay, we have a lot of approximate equations here, but I gave you one of them, right? Which is 0.1 n, okay, for steel building. And you determine damping ratio, okay? Damping ratio, something that you need to talk to somebody who knows damping, because damping ratio is not really calculated. It's just picked, select, okay, as appropriate to your building, right? And the buildings, the damping for buildings is different depending on how many floors you have, right? You have a low-rise building. What's the damping ratio? Around 5 to 10%? All right. What about the high-rise building? What's the damping ratio for high-rise building? 0.1% to 1.5%, right? Okay, so they're very different. Be careful, right? So this is a damping. Now you get calculate period, you get determine damping ratio. You go start looking at and entering x-axis with period you calculate in step 1, okay? And you're gonna meet a lot of curve, right? Like this. And you're gonna meet a lot of curve, but one curve is yours where you see your damping ratio, right? So your damping ratio, you select it like 10%. Then this is your, if you select your damping as a 2%, and this is your value, right? So when you select 2% damping, then your response is a little bit higher than that of on this curve, right? Because your damping is small, right? And you go here and get what? SA value in y-axis. What SA stands for? Spectral accelerations, right? Okay. And where after you get this value, now you're ready to use calculate earthquake force, F. Now you know how you calculate earthquake lateral force. Very easy, right? So earthquake lateral force are eventually calculated mass times acceleration. The acceleration is coming from y-axis of your response spectrum. So you are calculating to understand whole steps for response spectra. All right. Okay. Today's lecture is very important. Please, all of you, go and take a look at clip carefully and make a necessary memo and be ready for next clip. Next clip, I will be explaining the second way of getting earthquake force in Midas. So there we have, if you have to understand and calculate a lot of seismic parameters based on seismic map. We have seismic map, okay? So before we get into further theory, please be ready. Thank you very much for your attention today.